Concrete is everywhere. It's the literal foundation of our world, our cities, our bridges, our homes, but it has this fatal flaw. It cracks, it crumbles. But what if we could build with a concrete that was, well, alive? Something that could heal its own wounds, kind of like we do. Okay, let's get into it. And this right here, this is the heart of the mystery. Think about it. The Pantheon in Rome, still standing after 2,000 years. Meanwhile, a modern bridge often needs serious repairs within just 50 years. How did the Romans pull that off? And what can their ancient secret teach us about building the future? All right, so here's our roadmap. We're going to start with the concrete conundrum, then uncover Rome's enduring secret. After that, we'll meet nature's tiny engineers, see what the bioconcrete payoff looks like, and finally look at the hurdles and a new horizon. So first up, let's talk about the problem. We depend on concrete for pretty much everything, right? Yet it's a material that's almost designed to fail over time. It's this weird paradox that has huge consequences, not just for our wallets, but for the entire planet. And here is the biggest consequence of all. You see that number? The production of cement, that's the key ingredient in concrete, is responsible for a staggering 8% of global CO2 emissions. 8%! Every single time we have to repair a crumbling road or replace a building, we're adding to this massive environmental problem. The thing is, concrete is just under constant assault. You've got CO2 in the air weakening it through carbonation, you've got salt from roads or the ocean corroding the steel inside, and in cold places, water gets into tiny pores, freezes, expands, and basically breaks the concrete apart from the inside out. It's fighting a losing battle on all these different fronts. Which, of course, brings us back to the Romans. How on earth did their structures, we're talking about piers sitting in corrosive seawater, manage to survive for more than 2,000 years? Well, turns out the answer is in their recipe. It was fundamentally different from ours. So the key chemical difference is pretty wild. Modern concrete uses a binding agent that's, well, it's just not that stable in the long run. The Romans, though, used volcanic ash and lime to create this incredibly stable, durable crystalline structure. But that wasn't even their greatest trick. This is the truly amazing part. Roman concrete wasn't just stronger, it was smarter. They used a special hot mixing technique that left behind these tiny, reactive bits of lime. So whenever a microcrack formed and water seeped in, that water would activate these little lime pockets, triggering a chemical reaction that grew new crystals and filled the crack. It was literally healing itself. So fast forward to today, this ancient idea of self-healing is getting a 21st century biological upgrade. Instead of relying on little chunks of lime, scientists are now turning to something way smaller and way more efficient: bacteria. The science behind all this is called biomineralization, and honestly, it's happening all around us. It's the same process that lets coral build massive reefs or oysters create pearls. We're basically borrowing nature's playbook, getting specific bacteria to produce limestone, calcium carbonate right where we need it, right inside the cracks. So how does it actually work? It's this beautiful 5-step process. First, a tiny crack forms and water gets in. Second, that water is like an alarm clock. It wakes up dormant bacterial spores that were mixed into the concrete from the start. Third, once they're awake, they get hungry and start eating a food source, like calcium lactate, that was packed in there with them. Fourth, and this is the magic part, their waste product is pure limestone. Finally, that limestone hardens and seals the crack shut from the inside out. Now, of course, you can't just throw any bacteria in there. You need a specialist for this job. The microbes they use are true survivors. They have to be alkaphilic, which just means they love the super harsh, high pH environment of concrete that would kill most other things. They have to be spore-forming, so they can basically hibernate for decades, just waiting for a crack. And obviously, they have to be totally harmless to us and the planet. Okay, so we have this incredible technology, but what does it actually mean for us? For our world, the potential benefits are they're transformative. We're talking about a safer, cheaper, and way more sustainable world. First and foremost, our infrastructure will just last longer, a lot longer. By sealing these tiny cracks before they turn into huge problems, we can stop the rot, the corrosion and degradation that leads to failure. And that means safer bridges, more reliable tunnels, and buildings that truly stand the test of time. And of course, that extra lifespan translates directly into huge economic savings. Right now, we spend billions and billions every year on this reactive cycle of finding damage, fixing it, and eventually replacing the whole thing. Bioconcrete completely flips that script. The material maintains itself, which could slash those long-term costs.
And this brings us full circle. Remember that 8% figure from the beginning? If our structures last longer, we just don't need to make as much new cement for repairs and replacements. This directly tackles concrete's massive carbon footprint, turning our buildings and bridges into part of the solution, not just part of the problem. Now, as exciting as all this is, bioconcrete isn't showing up at your local construction site tomorrow. Let's be real, there are still some pretty big hurdles to clear before this technology can really go global. The main challenges right now are cost. It's still pretty expensive upfront, and making sure those bacteria can actually survive for 100 years dormant inside a chunk of concrete. It also has limits on the size of the cracks it can heal. But here's the good news. Researchers are tackling all of it. They're finding cheaper nutrients in industrial waste, designing tiny protective capsules for the bacteria, and even creating hybrid systems with polymers to fix bigger cracks. When you step back, we are right on the edge of a materials revolution. We're taking lessons from the ancient past and combining them with the power of biology to build a future where our world isn't so brittle and passive, but is resilient, adaptive, and, well, alive. And that leaves us with one final thought. What if our cities didn't just stand? What if they could heal themselves?